Hello, my pre-algebra students, and welcome to your first instructional video of the year, your first real one anyway, when we're not talking about like rules and how to ask to go to the bathroom and stuff. We're going to be talking about the real number system. And we're also going to talk about squares and square roots in conjunction with this. And without further ado, let's get started. First of all, how do we categorize numbers? There's a bunch of different ways that we categorize numbers. For example, odd and even. We learn about that pretty quickly. 2, 4, 6, 8 for our evens, 1, 3, 5, 7, etc. for our odds. That's one way to categorize numbers. Whole, okay, and not whole. We don't really have a specific word right now. We will in a minute for those fractions, okay? And in this class, real versus, well, we don't talk about non-real numbers. There are numbers that are not real. You'll learn that in Algebra 2, actually. But we're going to be talking specifically about real numbers, and being able to categorize them might be a useful skill when we're using them. This is a representation of the real number system, and this is the Venn diagram representation. So first of all, bear with me and let's describe it, explain it, what have you. So all the numbers we learn about are real numbers. And then from there, it breaks down into basically two categories: rational numbers and irrational numbers, and those are opposites. Those categories are opposites. When you take the rational number category, it breaks down into subcategories that get more specific as you go into these smaller circles, or ovals in this case. So this shows that relationship quite easily. So let's talk about some definitions, and I want you to recognize as we learn about them that one of these fits inside the next. So a natural number is also a whole number, it's also an integer, and it's also a rational number, and all the numbers we learn about are real. So let's take those categories you saw in the Venn diagram, and yes, you probably should copy it down, so rewind and go back and do it, please, if you didn't. Let's define them, starting with our natural or counting numbers. That's the whole numbers from 1 upward. So 1, 2, 3, and so on. And the ellipsis is what tells us that it continues on beyond that. Okay, then we have our whole numbers, which is 0 in the natural numbers, which would totally be my band name if I ever started a band. And that's 0, 1, 2, 3, and so on. And you can think whole numbers starts with the number with a whole in it, right here. Then we have our integers. Integers would be if you started out at negative infinity and you counted only the numbers with no bits and pieces, so no fractions, no decimals. So you notice my ellipsis, negative 3, negative 2, negative 1, 0, 1, 2, 3, and we have the ellipsis on both ends saying all the way up and all the way back and all the way up. So this is our number line numbers. I sometimes think of our integers as our number line numbers, because those are the only numbers you would logically put on a number line. You're not going to put 3/7 on a number line. Rational numbers can be written in fraction form. So that's going to include positives and negatives, because you can write fractions like negative 4/7. There's a fraction that's negative. So, and positive fractions like 1/10. But it also includes any number that can be written as a fraction. The number 17, for example, could be written as 34/2. And that is 17. That can be written as a fraction. And that's one of those things that helps us understand that all of these categories below rational numbers, they all fit into there. Because I can write 1 as a fraction. I can write negative 2 as a fraction. I can write 3 as a fraction. So all of these categories fit into that rational numbers category. The other thing that you want to understand here is that repeating decimals are included in this, because you can write a repeating decimal as a fraction. Okay, that is a confusing thing to understand, and I'm going to show you some tricks with that in class, but you can write a repeating decimal as a fraction. Finally, you have your irrational numbers. They're non-repeating, non-terminating decimals. And we're going to learn a little bit more about these on a future slide. These cannot be written in fraction form at all. Here we have a tree map, and a tree map is another way for us to show these relationships. The real number category splits into two parts: rational and irrational. And then under rational, you get your more specific categories going down. It's similar, very similar to the Venn diagram, but it shows a different way of organizing. It's a different way of showing the hierarchy of these categories. So if the Venn diagram doesn't jive in your brain, try the tree map on for size and see if that's a good way to understand the relationships between these categories. Let's talk a little more about the irrational numbers. First of all, they totally confounded early mathematicians. They really did not have a clue. Like, these guys could figure out that if you took 9 little stones, just pretend they're little stones, that you could put them in a square, but if you had a 10th one, you couldn't make a square. So they could figure out some of these things, but they couldn't figure out irrational numbers. So our irrational number system, it includes numbers like pi, and we know pi as that famous number that we celebrate on March 14th, and it has something to do with circles, but we'll learn more about it this year. So irrational numbers can be these, like pi, non-terminating, non-repeating decimals, as you wrote down before. But it also can include these weirdo decimals that just have a pattern, but it's not a repeating pattern, like 0.01, 001, 0001, and so on. And then what other numbers are irrational numbers is the square roots of non-perfect squares. And we're going to talk more about these in a minute when we define what perfect squares and square roots are. Let's define these perfect squares and square roots. A perfect square is a whole number whose square root is a whole number. Now when we say square root, the square root of a number is asking you what times itself. What number times itself will equal that number on the inside? That's what the square root is asking. So perfect squares are ones that you can give me a whole number to answer that question. 1 is a perfect square because 1 times 1 is, that's right, 1. 4 is a perfect square because it's 2 times 2. And let's list them all the way up to 400. Okay, 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 6 times 6, 36. 7 times 7, 49. 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. 11 times 11, 121. 12 times 12, 144. 13 times 13, 169. 14 times 14, 196. Oh, this is starting to really tax my brain. 15 times 15 is 225. 16 times 16 is 256. And I've just about stalled out, so I'm going to have to break out my handy-dandy iPhone calculator. And I know I'm probably not supposed to use a calculator, but do you know what 17 squared is without a calculator? I didn't think so. 289. 18 squared is, I think, 324. It sure is. 19 squared, I'm almost out of space, is 361. And finally, 20 squared is 400. And there's all your perfect squares from 1 to 400. Okay, so as we define square root of a number, that's what we were talking about up here. It's the value that, when multiplied by itself, gives you that number. So the square root of 289 is 17, and we'd write that like this. Square root of 289 equals 17. Now, if you have a number that is not a perfect square, the square root of a non-perfect square number is automatically irrational. You can't write it as a fraction. It's a non-terminating and non-repeating decimal. The only reason what you see on the calculator screen ends is that it's a piece of equipment that only has a screen that's so long. So when the screen ends, the number has to be cut off, and the calculator is actually rounding it off for you. So you're not actually even seeing the correct digits there at the end. So if we know a number is not a perfect square, but it's in a radical sign, so this really should say locating square roots of, fixed it, locating square roots of non-perfect squares on the number line. So if I know a number is not a perfect square, but it's in a square root sign, I can only find it with a calculator, right? Well, yeah, kinda. There actually is a cool way to find out the approximate value of a square root without a calculator. And we can at least locate a square root without a calculator. So this is something we do need to know how to do, and this is why you have to know your square root, your perfect squares from 1 to 400. So any whole number that is not a perfect square has a square root that lies between two consecutive whole numbers, or in this case, integers. for the third one I gave you because it's negative. Now let me explain, okay? The square root of 57 we can find approximately the value of with a calculator. But what I can definitely say is that because the number 57 is bigger than 49 but smaller than 64, then that means the square root of 57 is between the square roots of 49 and 64. And the square root of 49 is 7, and the square root of 64 is 8. So the square root of 57 is somewhere in between those two numbers. It is ever so slightly closer to 8. It's ever so slightly closer to 8 than it is to 7, because 57 is just a little bit closer to 64 than it is to 49. Let's try another one. Look at the second one on our list here, square root of 15. The square root of 15, I'll do it in blue, okay, down here. 15 is larger than 9, but smaller than 16. So the square root of 15 is going to be larger than the square root of 9, which is 3, but smaller than the square root of 16, which is 4. Which one is it closer to? If you answered 4, you answered right. And no, I can't hear you. I won't do that nonsense where I pretend to hear you. This isn't Blue's Clues, people. So anyway, the square root of 15 is very close to 4, because 15 is very close to 16. And then let's look at the last one. The negative square root of 105. Well, first of all, let's get rid of the negative part. I think I went a little too quickly with that, so let's pretend it just said the square root of 105. If you want to talk about the negative part, we can talk about it in class individually. The square root of 105. Well, 105 is bigger than 100, and it's smaller than 121. So that means the square root of 105 is bigger than 10 and smaller than 121. And I just barely fit it into the space I had there. So at least now you can locate non-perfect squares on the number line. Alright, so one of our skills we're going to be working on this year is being able to locate the value of a number on a number line. Now we just went over how to do that with square roots of non-perfect squares. I'm going to pause it and I'm going to give you a smattering of different kinds of numbers, and I'm going to ask you to lay them out on that number line where they go. So let me pause it, and here come your numbers. Okay, there you go. There's 10 numbers. I want you to draw a number line that looks like mine. I want you to take that number line. I want you to put these numbers in order on that number line, and I want you to pause it. I want you to do this by yourself. I'm going to go through and do it as well, and I'm going to go through and do it rather quickly so we can wrap this video up for you for today. So pause it. I mean it. Pause it, please. Try it yourself. Okay, let me have at it. All right, let's start with my natural numbers. 6. There's 6 right there. I'm going to underline them and color code them here. All right, and guess what, guys? That's the only... nope, there's one more natural number. The square root of 4. The square root of 4 is actually just 2. The square root of 4 is just 2. All right, and make those dots a little bit more manageable sized. Okay, so now let's switch to a green whole number. There's only one number up there that's whole that's not also natural, and that is 0. And there it is in that nice lime green color there. Let's use red for our integers. We have a -1. -1 is going to be located right there. We have a -16/2. That's -8. And that's an integer. Okay, so notice that is equal to -8, and that's where I put it. Now, -3.4, not an integer. Not an integer. That's a rational number. So we'll come back to that. Just because it's negative, remember, doesn't make it an integer. 1/4, 1/4 of the way from 1 to 2, right there. -3.4, less than -3, but not quite closer to -4. Still a little bit closer to -3 than to -4. And then 5/8. 5/8 is a little bit bigger than 1/2, so that's going to go right there-ish. And then finally, we have our irrational numbers. Pi is a little bit bigger than 3. And there's pi right there. And 26, square root of 26. Well, square root of 26, that's going to be between the square roots of 25 and 36. So that means it's going to be between 5 and 6. A whole lot closer to the 5. We'll put it right there. And that, folks, Gets you all the way to the end of your first instructional video in pre-algebra this year. I hope you enjoyed it. Bring all your questions to class and be prepared to apply all your new knowledge. See you in class.